Hello, calculus students. Welcome to the lesson on antiderivatives. If you're studying with Mr. Wen, you have now proved the fundamental theorem of calculus, and you see that it involves finding antiderivatives, so that makes our lives easier. Plus, let's face it, who doesn't like finding antiderivatives? So we have to get into the hang of finding antiderivatives, and this is all mostly mechanical, that requires lots of practice. But I'm sure with practice you will be able to do it. Okay. So first problem, the definite integral from 0 to pi of sine. Well, we got to ask ourselves, what is the antiderivative of sine? And that is, of course, cosine. We want to evaluate this from 0 to pi. Ooh, I'm sorry, this is negative cosine. Almost messed that up and lost the point. So this is then equal to the negative cosine of pi minus the negative cosine of 0. Cosine of pi is, of course, negative 1, so you have negative 1, minus cosine of 0 is 1, so negative 1. So this is basically positive 1 plus 1, which is equal to 2. Okay. And we, of course, want to use proper notation. This notation here with the bar, the lower bound, the upper bound, is just the evaluation at these using these two values. Okay. Now, without this thing here, remember, without the bounds, this is called the indefinite integral. So it's just really looking for the antiderivative. So we've got to ask ourselves, what's the antiderivative of cosine? Well, that is, of course, sine of 5x. Okay. But we get to take the chain rule into consideration, because when you take the derivative of sine, you end up with the 5 in front. Right? So if you do in fact try to take the derivative of sine of 5x, you end up with cosine of 5x times 5. Okay? So in order to undo and wipe out this 5, we got to multiply by 1/5. And because this is an indefinite integral, we're looking for an antiderivative. There are many solutions, and you need to include c there as your constant. Okay. Moving right along, the antiderivative of e to the x is wonderfully just e to the x plus c, because, remember, e to the x is its own derivative, which means it is also its own antiderivative. Next example kind of combines that idea from number 2 and number 3. So this is going to be the same thing, e to the 5x. However, remember that when you take the derivative of e to the 5x, you get an extra 5 in the front. So in order to get rid of that, you got to multiply by 1/5. So generally speaking, when you take the antiderivative of e to the kx, where k is a constant, this is going to be e to the kx times 1 over k. Next here, we have a beautiful definite integral. And this also has a geometric meaning so that you don't entirely forget. This is from 2 to 3, that area. So this is the antiderivative of e to the negative x, which is e to the negative x, times negative 1, because you're going to need that when you take the derivative. You end up with a multiplying by negative 1 from 2 to 3. Okay. So this will become a negative e to the negative third minus negative e to the negative second, which will become e to the second minus e to the negative. This should be the negative second and negative third. Just for some good practice, when you inevitably will deal with multiple choice questions, you will probably see this as 1 over e squared minus 1 over e cubed, which may sometimes be rewritten as e cubed minus e squared divided by e to the 5th. Okay. So any of these versions is correct, but you might see different versions of this on the the AP Calculus exam. Next one, we have the indefinite integral of 1 over x. Now you might be tempted to say that this is just x to the negative 1 dx, and then you might try to go, well, add 1 to this, so that's x to the 0th divided by 0th, which is a problem. Okay, so this rule of taking antiderivatives with polynomials, it doesn't work when you have 1 over x. But remember, the derivative of some special function is 1 over x, and that special function is, of course, the natural log of x. Okay. But the natural log of x is only defined when x is greater than 0. Okay. So, and 1 over x is defined for x greater than 0 and x less than 0. So we have to make sure that these adjustments get made, and this absolute value symbol has to apply, because it's really natural log of x for positive x values and natural log of negative x for negative x values, plus a constant. Ooh, I forgot my constants up here. Hopefully you thought of that. Okay. Another yet tricky example here, number 8. Let's say we want to take the antiderivative of all of this. This is one of those nice examples where you could separate this into x over 7 over x squared minus 3x over 5 over x squared plus 4x over x squared dx. If you try and take the antiderivative of this as is, you're reversing the quotient rule, which will lead you to a very, very large mess. So separating it allows us to break it down into these much simpler polynomial-like expressions, which will then allow you to evaluate this a lot better. So this right here is x to the 6th times 1/6 minus x to the 4th times 3/4 plus the antiderivative of 1 over x is, of course, the natural log of the absolute value of x times 4 plus a constant. Okay. So when you have complicated rationals like this and it's possible to split it up, I would go ahead and split it up. So that's much, much simpler to deal with. Okay. Let's do number 9 over here. Now you have the antiderivative of tangent squared plus 1. Okay. The antiderivative of tangent squared is pretty difficult to find, but you want to exploit the fact that tangent squared plus 1 is in fact equal to secant squared. Realize there's a typo in my notes here. It should be pi over 6 to pi over 3, not 0 to pi over 3, d theta. Okay. So here you really have to understand trig identities, and you really have to understand derivatives of trig functions. So this will be tangent theta, because that's the derivative of tangent is secant squared. So this is tangent theta evaluated from pi over 6 to pi over 3. I hope you're good with your unit circle. This is going to be, you got to find out what is the tangent of pi over 3 minus the tangent of pi over 6. Okay. Well, tangent of pi over 3 is the square root of 3, and the tangent of pi over 6 is 1/2 divided by root 3 over 2, which is root 3 over 3. So this is 3 root 3 over 3 minus root 3 over 3, which is 2 root 3 over 3. Ooh, just squeeze that in there. All right. So there you go. That was a very brisk moving pace through all of these different examples, but I wanted you to be able to see them so you can see all the different tricky parts. Antiderivatives, now if you understand the fundamental theorem, is incredibly useful, and for the simpler ones you can just use your wonderful mind to undo and reverse the process, but you really have to be careful with some of the more tricky examples here, where you have a constant that you have to adjust by because of the chain rule. Same thing here with e to the x, and especially with natural log. Try your best to convince yourself and understand why this is true. Don't let your teacher leave the building until he explains it to you why this is true and you fully understand it. Thank you for watching, and have a wonderful day.